screen. 1 second. Okay, good. Very good. So how are you? Everything is fine? Okay, very good. So first, I just wrote, as you noticed, on the Teams chat about some details. Tomorrow lecture for those of you who are attending the lab is online only. So it is in the virtual room. You have the address under virtuale. We meet at I start as here 11:15 in the morning. And then I start at 2 sharp in the afternoon. And again, online only, because I think it's better if we, tomorrow, for what I would like to do, it's better if we interact through the PC, because I can share the screen with all of you, and it's more handy, I think. And then I sent some details about the exam for December 22nd, is in Aula Disegno. I think, I'm not sure if Serena replied to you already. Yeah. But yeah, she told me that this is fine, and she will tell you where you need to meet with her on December 19th. Okay. Perfect. And then I didn't book the room for the exams in January, because I will book it in December, after I realized how many of you take the exam on December 22nd. The exam, I think it's not yet on Alma Esami. I need to book it, and because I needed to know the room first. And then I think everything is all set. The exam in December will be here, of course, in physical presence. As you know, it's not possible to take the exam online. And in January, we will see whether the exam is in Ravenna or Bologna, depending on, as I said, on the students who have to take it. Of course, we are willing to come here, as you noticed from Serena. I need to remember also to post on Virtuale these details, and I will do that. But I think you all are on Teams, and I hope you got the message already. But I hope I remember also to send it on the forum on Virtuale. Any question related to this? Okay, perfect. And today, if you remember, we finished the last lecture working on R, and we worked on estimation of trend for a time series. So, as you see on the screen, we developed a trend estimation in some way on some data. I don't remember which data we used, but here I want to get back to the point where we closed the last lecture. So I generated just a random series with a sample size of 1,000, and now I am estimating a linear trend over it, because I want to get at the same level where we got last lecture, as I said. Of course, this is completely random, so I am expecting a slope of something like 0, around 0, and also the intercept is around 0. So let's take the estimation. So linear, let's call it linear reg, okay? It's, as you may remember, LS fit is the R function. And now we need to give the X variables, because it's a regression along time. So the dependent variable is what I generated, series 1, that you see on the screen. This is the dependent variable. The independent variable is time. Okay, and so to generate the independent variable, which I need to give as first argument, I make a sequence from 1 to 1,000. Okay. And then I can give the dependent variable, series 1, and I think that's it. Now, very quickly, last time, I said that the output from this linear regression is a list. What is a list? It's a group of R variables, and this group may include character variables and numeric variables. And the list is an idea for putting information together under a single name, which is the name of the list. And so you have a lot of information in the result, which is called linear reg. And in fact, if I just type linear reg, you get something scrolling on the screen very quickly. So it's impossible to get an idea of what's going on because the scrolling down was very quick. So to get an idea, when we deal with lists, what I suggest to you, now I clear the screen because now the screen is busy, okay? My suggestion is to use the function names, names of the list, because the list it's like a catalog, and in order to identify what's inside the list, R uses the solution of giving a name to each variable that is inside there. So if you ask for the names, you get these names, and beware, some of them may be lists. So it's not even for granted for sure that these are like numbers or text. They may be lists, okay? So let's try, even that we see here coefficients, let's try to see what is under coefficient. And if you want to visualize a list with the corresponding name coefficient, you have to put a $sign and then coefficient. I use the tab, you see that it's completed. And here are the coefficients. So the intercept, which is basically 0, as we expected, and the slope is called here x, and the slope is close to 0, as we expected. You see that the result under coefficient is still a list, okay? And indeed, it displays names because it's a list and what is under the name. So if I want to get only X, here I have to put $X. Sorry. I think it doesn't take, let me see. Yeah, it doesn't take a nested, so I think this is actually not a list, it's a data set. So the data set is another way of grouping variables into R, and the data set is like a table. And the table, there is the heading, and the heading here is, one heading is intercept, the other heading is X. We don't need to go into details, okay? I just want to give you for now an overview. So don't ask questions to yourself like why they decided to make a list and a data set, what's the difference? Let's not go into the details now. But if I want to visualize X as a number, what I have to do is to use this way of displaying it. Because double squares means go into the data set and get the number. Sorry, this is actually number 1 is intercept, number 2 is the slope. Okay, and so now the question is, and this is also the theoretical question that I want to explore with you now. How can I say safely that intercept is 0 and the slope is 0? Because here it's not 0. It's very close to 0, but it's not 0. Okay, so how can I say if, again, the question, intercept is 0 and slope is 0? First, this is a question, a statistical question, you know. So we shouldn't say in statistics, we already said that, we shouldn't say, how can I say that the intercept is 0? We should say, how can we not exclude that the intercept is different from 0? Okay, so I repeat the question. How can we not exclude that the intercept is 0? Why we say like this? Because in statistics there is uncertainty. Otherwise, we wouldn't use statistics. Okay, and so if there is uncertainty, I cannot say something like, "How can I say that intercept is 0?" So because the meaning would be actually, how can I be certain that intercept is 0? And this is not correct if you have uncertainty. So the correct way of saying it, also grammatically and colloquially, is how can I not exclude that the intercept is 0? And then you understand there is uncertainty. The implication is there is uncertainty because I'm not saying this is the value. I'm saying that I exclude the not values, which means that there is uncertainty. Okay, perfect. Now, how can then we reply to this question? Okay, to reply to this question, it's important to start from a premise. First, let's make it, let's clarify it in an informal way. If there is uncertainty, it means that I have to reply the question how not to exclude. I have to make clear what is my confidence in what I am saying. So, what do I mean? When you are uncertain and you make a prediction, you always have to specify what is the uncertainty that you feel in your prediction. But of course, if there is uncertainty, you have to quantify to what level you are uncertain. Like, for instance, when we look at predictions for outcome from elections, they say, I am 95% sure that the winner will be. So this means quantification of the level of uncertainty. Of course, if I, and this is not really a good example for what I want to convey, let me make another example. If I make a prediction for rainfall tomorrow, okay, so probably tomorrow will be 0 rainfall in Ravenna, I can say, okay, I am 95% sure that rainfall tomorrow in Ravenna will be between 0 and 1 millimeter, okay? Because there is uncertainty, so I have to admit that. So, but if you want to be not 95, but 99% sure, of course, the range has to increase. So I should say, I am 99% sure that rainfall tomorrow in Ravenna will be between 0 and 2 millimeters, larger, because I want to be very conservative, okay? So, of course, when I specify, then I go back to the linear regression. Now, what I have to do is to specify a range around 0 for both these two variables, intercept and slope. And this range around 0, which can be negative, I mean, the lower range is negative because it's around 0. So I expect that the range will be delimited by a number that is less than 0 and a number that is greater than 0. This range, if I want to be like 95% sure, will be like this. If I want to go to 98%, be like this, 99, like this, 99.9, like this, never 100. But you can say 99.9999999, and it becomes larger and larger, okay? So this level of confidence is precisely called confidence level. So when now we estimate the range around 0, we have to specify what is the confidence level that we want. Let's go to Wikipedia and see under confidence level what Wikipedia says. And I'm sure that if I just Google for confidence level, I go to Wikipedia, I think. Let's see, confidence interval. Okay, yeah, okay, there are many synonyms. Okay, so confidence level, confidence interval. I mean, actually, confidence interval is precisely the range. The confidence level is the level of uncertainty. So they are not really synonyms, but more or less. And indeed, let's go, let's see if there is an entry for Wikipedia for confidence level. I would say that there is, but let's click on confidence interval. So, and you see here, in statistics, a confidence interval. One thing, when you see in Wikipedia this warning, just read it and be careful, okay? Because it means that somebody said, you know, when they reviewed it, Wikipedia is reviewed by experts, and they are usually volunteers. When they have doubts, they write this warning. And you see, this article needs attention from an expert in statistics. The specific problem is this article may be too technical for most readers to understand, which, I mean, it's not really a big concern for us because we want to be technical. But on the other hand, the general message that I want to convey, Wikipedia is great, but pay attention to these remarks. And if you are even more interested, you click on view history and you see a description of all the development of this article. And there are also the discussion. You see here, the reason given for not changing the wording here is not true, and the source cited in the edit summary does not make this claim. Okay, so it's interesting. Sometimes I had the opportunity, I was curious and I wanted to know what was the concern, and I looked at it. Okay. Be careful, because this is something that when you go to ChatGPT, it's not really these warnings, you don't get them. And I go back 1 second. Here there was, an artificial intelligence overview. I think here, I think it's correct up to here. Okay. I think here, it's not really, I mean, it is written in a way that is understandable, but it's not formally correct what's written here. It is expressed as a percentage. It's not a percentage. Okay, the confidence level is a percentage, but I mean, it's not really the best way to say it. Wikipedia. Now, let's see if there is a link to the confidence level, because you see, in statistics, a confidence interval is a range of values used to estimate an unknown statistical parameter, such as a population mean or an intercept or a slope. Rather than representing a single point estimate, okay, a confidence interval provides a range along with a specified confidence level. Okay, typically 95%, this is something arbitrary. I mean, it's not true that, yeah, it's correct that typically it's 95%, but it's, I mean, it's, you can change it, okay? So here you see that it says a 95 confidence level. That does not imply a 95% probability that the true parameter lies within a particular confidence level. And yeah, the confidence level instead reflects, because now we have to understand what is the confidence level and provide a definition for it. Okay, let's see what they say here. The confidence level instead reflects the long-run reliability of the method used to generate the interval. In other words, and this is what is interesting to read, if the same sampling procedure, so if the same linear regression estimation was repeated 100 times from the same population, approximately 95% of the resulting intervals would be expected to contain the true population mean. So let me translate it in our case, okay? Now, remember, it's, can you please, I am teaching, can you please avoid to speak, please? I'm sorry, you should avoid to speak, thank you very much. Yeah, so let me repeat, make it with reference to our example, okay? So let's first remember the words. If the same sampling procedures were repeated 100 times, approximately 95% of the resulting intervals would be expected to contain the true population mean. Okay, very good. Now, let's go here. And let's generate another random time series. Okay. And now I repeat the estimation of the linear regression. And now I visualize the intercept number 2, the slope. You see that the value is different, okay? Because I made another sampling from the same population. What is the population? The population is the normal distribution with mean 0 and standard deviation 1. So from this population, I can make many samples, okay? And let me clear the screen. I could repeat 100 generations. This is just one. 100 estimation of linear regression, 100 of this, okay? No, it's not 100. This is the third that I'm doing. I should repeat other 97 times, okay? So let me make it indeed 100 times through a 4 cycle, okay? First of all, if I make it 100 times and I am interested in the slope must be stored into a vector, because at the end of the 100, will take 1 second to generate 100 of these sampling, but each time I have to keep memory of the result. So let me define slope equals 0, define a vector. This is a variable now, but I can use it as a vector, okay? And then I make for E in 1 to 100, okay? Now I need to, sorry. Yeah. Now I need to open a parenthesis. I never remember how to do that. Just a second. I will get it. Give me some, just one. Okay, not, I think it was Alt Shift 7. No, let me see. Ctrl Shift Alt 7. No, Alt Shift 7. And so Alt. Yeah. Let me see. Okay, good. Alt GR Shift and square bracket. Okay, now let's make. I get back the generation. Linear regression. Good. And then I get back. Oh, sorry, I was wrong. I forgot the linear regression. So I think I can leave it there. It's not a problem. Let me get linear regression. So this instruction here, it's not needed, but I can leave it there. It's not a problem. Okay. Now I have to make, to get it back, and make slope I, it's equal to this, and then I can close the parentheses and Alt Shift. Okay, is it clear what I did here? And beware, this is not necessary. Okay. Now let's make it. It's terminated. Okay. So let's see the vector slope. I clear the screen. Slope. Okay, this is the list of the results. Let's make a plot, just because otherwise, I mean, plot slope. Okay, here is the plot. Okay. Now, let's identify, remember what we said earlier. We made the sampling 100 times, and let's identify the range such that 95% of the numbers of the resulting slopes are included in the range. Okay. And in order to do that, it's very, let's say that it's not very easy, because 95 divided by 2 is not an integer. Let's compute the confidence level, the confidence range for 94% probability. So first of all, let me clear the screen. What I have to do is to order the slope. Slope equal order slope. The order means it's ranked in ascending or descending. I don't remember. Not actually. So let me see. It's not order, but it's. I tell you. Slope equal. It's not ranked. Just 1 second, because I don't remember. I need to make a quick check over Google. Okay. So data our project. Our project. Yeah, order. Okay. So sorting data. I think sorting data. Let me see. Decreasing true or false. I think should be ordered. Let me see in the numbers, because otherwise it's not easy to see. No, this is something that it's not good. Because it gave to me the index of the vector that I need to put the data in ascending order. The problem is that this is fine, but the problem is that now I overwrote the vector slope, the results, so I need to repeat the sampling. Is this clear? I made a mistake. What I did with the function order is to identify the index of the vector to put it in ascending order. What does this mean? 41 is the index of the vector slope, previous vector slope, where the lowest value is. 92 is the second lowest. 85 is the index of the third lowest. The problem is that I overwrote and let me just see, because I think the function that I should have used actually is sort, I think. Sort or order. Sort, yes. I should have used this one, not order. Order gives the index of the vector. Sort is indeed ranking the data. Okay, no problem, because it's very easy to remake the for cycle. Let me go back. For, okay, perfect. Now I need a bracket. And so we can also forget this. I need to series generate. Now we can forget this one, make the linear regression, and then we have to assign this one, and then I get the bracket. Good, here we are. So let's make now slope equals sort slope. Let's see if now I made it correctly. Plot slope. Okay, here it is. You see that now it's in ascending order. Okay, so now let's identify the range at the 94% confidence level. It's very easy. The lowest is slope 3. And the upper is slope 97. So this means that you have 94 value of slopes that are included in the range minus 0.0022 plus 0.00020. Okay, so if you have included in this range 94 variables over 100, it means that you have a 94% probability of getting the result into the range. Okay, if I wanted the confidence level for 80%, sorry, the confidence range, confidence interval for 80% confidence level, it's very easy. I have to exclude 20 results. And you see that it's a bit smaller. This is very clear. So now we understand what is the confidence interval. It means that if the resulting slope is inside one of these two ranges, let's take the first one, it means that I cannot exclude that the resulting slope is 0 at the 94% confidence level. Okay? So if I look at the second range, it means that if the slope is inside the second range, it means that I cannot exclude that the resulting slope of the time series is 0 at the 80% confidence level. Okay, so basically try to follow me with an example of climate change. Suppose that you get rainfall in Bologna and you estimate the slope of the rainfall in Bologna a long time, daily rainfall. Okay. So let's suppose that the resulting slope is within the range that you estimated for 0 value at the 95% confidence level. So my conclusion is that I cannot exclude that rainfall in Bologna, daily rainfall, is not affected by any trend at the 95% confidence level. Okay. It means that, be careful, there is still a 5% probability that my conclusion is wrong. So there is a 5% probability that I reject the null hypothesis. This is another statistical terminology. What is the null hypothesis? The null hypothesis is not there. So there is still a 5% probability that I reject the null hypothesis of no trend if this is true. So this is typical statistical terminology, which is very boring. But on the other hand, I wanted to discuss with you because when you estimate if there is a change or you estimate a parameter and you are interested in determining uncertainty, it's necessary that you understand this terminology. Okay? And so the 95% is the confidence level. The remaining 5% is called the significance level. Okay? And I mean, I tell you, every time that you need, also with structural mechanics, with you estimate a load, and there is uncertainty, and you are required to quantify uncertainty, anytime you have to define a range. So you estimate a load, and you don't give a number. If you're required to identify uncertainty, to estimate uncertainty, you have to give a range. So plus minus 2. But if you give the range, you have to specify either the confidence level or the significance level. They are the same thing. They are complementary to 100% each other. And so be reminded that any time that somebody will tell you about uncertainty, they should give this kind of information. We are talking of uncertainty of a number, of a parameter. We are not talking here, of course, we are talking of uncertainty of variables. We are not talking of uncertainty about statements. But you can generalize also to statements like, I think tomorrow will not rain. At the 95% confidence level, it's not very, it's colloquial. It's because, you know, will not rain, meaning that you are giving a number. But for you can also quantify uncertainty of a statement, but it's this what I define is uncertainty for a variable. Okay, and you will be always given this kind of information. Sometimes when you look at the methodological prediction, and they want to be colloquial, they want to be understood. So they will give you a prediction. And then at the end they say, reliability, estimated reliability of the prediction, and they may give a percentage. And like, it will rain 20%. Or so rainfall may occur for 20%. This is not statistical terminology, but now you can understand what is the meaning. It means that they, if they say it will rain 20%, it means that they estimate the rain for tomorrow, confidence interval, and with a significance, with a confidence level of 20%, they can say that it will rain. Okay, so it's greater than 0. And it's colloquial, but now we understand what is behind it. Behind it, there is an estimation of confidence interval for a given confidence level. And you understand what it means. Okay. Now, the problem is, you should ask me, yes, you estimated the confidence level here, the confidence, interval here for a given confidence level for the regression, but you had to perform 100 trials, okay? And you may ask me, but if I have only one time series, rainfall in Bologna, how can I estimate the confidence level? I need an indication. I need somebody giving it to me. Okay. Good question. Now let's clear the screen and remember that I have here a result from a linear regression, which is called which is called something like linear reg. Okay, linear reg. Okay. And now linear reg coefficients 2. This is the last slope that I estimated. Okay, let's suppose that we have only this one. How can I get the confidence interval if I have only this estimation? Okay, let's see one possibility. Okay, one possibility to make it. Let me clear the screen again. I can keep it on there. So let's see, diagnostic. R gives to me the possibility of diagnosing the linear regression, which means that R gives to me the confidence interval. Let's see, diagnostic is equal to ls.diag linear reg. So basically, this is a function, ls.diag is a function that computes the diagnostic, and it requires only one argument, is the result of the linear regression. Perfect. Probably it's a list. Let's see. Names, diagnostic. Okay, let's see several names. Let's look at, I think, looking here, maybe I am interested in std.r. Let's see. Names, diagnostic. $std.r. Good. Okay, fine. It looks like something interesting. It says intercept gives a value and x gives a value. And given that it's called std.r, I think probably these are standard errors. Indeed, if you look at the help of the function, it tells you this is the standard error of the estimation. Now, what does it mean, standard error, and how can I compute the confidence interval given the standard error? Okay, the standard error is the standard deviation of the estimation. We know what is the standard deviation. First of all, we see that it's very small. But how can we, from the standard deviation, compute the confidence interval for a given confidence level? Okay, perfect. Now, remember that we need to make an assumption. So given that we are given a standard error, a standard deviation, and we are not given a skewness or asymmetry measure, we need to assume that the underlying distribution is normal because we are only given a second order property. So let's assume it's normal. And let's make this assumption. And what is normal? It's normal the population of the estimate. So it means that I am assuming that my vector slope that I previously estimated is normal. Okay. First of all, let's make a small check. Let's see if it is normal. Okay. So plot density, slope, type equal line. Yeah, it's fairly normal. Okay, fairly normal. Perfect. And indeed, this is an assumption that is often made in linear regression. So it is assumed that the estimates are normally distributed. And it can be proved that the estimates are normally distributed if the data, the original data, what I sampled, is normal. Because remember, the normal distribution after linear transformation is preserved. So it means that if the original data are normal, the error of the linear regressions are still normal because it's a linear transformation. When I pass from the data to the errors, it's a linear transformation. And it can be proved that also the resulting estimates are normal. If I start with the log normal, you can try, you will see that the resulting estimates are not normal. But in this case, it's normal. So let's introduce this assumption. But keep in mind, R doesn't tell you, but R is, when it gives to you the diagnostic, R is assuming that everything is normal. And if you look at the help, it is specified this. And remember that if the series is not normal, it's a problem. So you don't have to trust the standard errors of R if the series is not normal. In this case, it looks normal, okay? So how can we estimate the confidence interval for a given confidence level? Well, let's say that if you compute this quantity, 1.96 times, it was, the result was linear reg, and then, no, it was diagnostic. Let's see, diagnostic, and then STD R. I think it was the number 2. Let's see. So what I did here is, let me just show you. Once again, the vector diagnostic standard error. Yes, so the standard error of the slope was 0.301. If I compute it by 1.96, I get 0.3021. Let's look at slope 97. You see, it is the same, more or less the same. So it means that if I multiply diagnostic for 1.96, I get, if I plot the standard error times 1.96, I get indeed the good estimate for the upper confidence level. The lower confidence level is just 1 minus. So indeed 1.96 is the good number, but what is 1.96? Let's see. If I compute quantile normal, which means the inverse of probability, of 0.975, this is 1.96. So I made the assumption that the underlying distribution is normal. So let's, if it is normal, let's see what is the corresponding quantile for probability of 0.975. I looked earlier for the 97th value, and it means 97th value, it means probability of not exceedance of 97%. So now here I am computing the normal number, which corresponds to a probability of 97%. That forgets the 0.5. Okay? And indeed, I see I get 1.96. It means that in a normal distribution, I'm looking for data that for a probability of 95% are included in the range. And you may ask, why 97%? You said 95. Yeah, because of course 95% probability means that I have to exclude, to cut off the lower 2.5% and the upper 2.5%. So if I cut off the upper 2.5%, I have to look for probability of not exceedance of 97.5%. So this is the rationale. So basically, you make an estimation. If you are given the standard error of the estimation, and the standard error is computed according to a theory, which we forget. I mean, we only want to know the assumptions, and the assumption is normality, Gaussian distribution. So the standard error is given through a theory, fine. And then through the standard error, I can compute confidence interval for a given confidence level. Okay. In terms of terminology, it's very boring. I hope that by doing it on the PC, you can get some more fun. Okay. Now there is a remaining question, and then we close this discussion. The remaining question is, what if the distribution is not normal? Rainfall in Bologna is not normal. So how can estimate the trend? Okay, let's suppose that I have this rainfall in Bologna and clear the screen. I could also upload it, but let's save time. Okay, let me generate like rainfall Bo is again R norm, but this is not just 1,000. Rainfall in Bologna is like 200 years, more than 200, but let's assume 200 years. And then daily rainfall, it means that it's long, something like this, okay, 70,000, 72. I have this rainfall in Bologna, and then I can estimate the slope. So let's make slope 1. Let me overwrite it. I make this estimation. Slope 1 is equal to LS fit rainfall Bo. Okay, and then here I have to make it's just fine if I put the first letters too. Okay. Yeah, correct. I should put here sequence 1 and 30 times 2. Okay, what's wrong here? It's missing a parenthesis, so, yeah, there is a mistake, sorry. There is a mistake because I put here not a 2, but, okay. So I estimated the slope of the rainfall in Bologna. It's in slope 1, so slope 1. It's not normal because, okay, here in this case, it's normal because I generated from a normal distribution, but in general, it's not normal. So how can I estimate the confidence interval? Because I have only one series, I cannot sample so many times. There is a very simple possibility for doing that, which is called bootstrap. I didn't know when I had when I first applied it, but it's bootstrap. It's a very known procedure. And bootstrap is done in this way. I have only one time series, and I am testing whether the time series is affected by trend or not. So I can generate a similar time series by simply doing this. Rain sampled is equal to sample rainfall law What is the range sampled? I simply shuffle the data, I mix them. So when I take a time series and I mix it, like in Italian we may say la metto nel frullatore, I put it in a shaker, okay? I preserve the probability distribution because the probability distribution is preserved because they are the same numbers. On the other hand, I destroy any correlation and I destroy any trend if there is a trend. Because, of course, by shuffling, I destroy the trend. So the resulting time series sample is for sure without trend. And therefore, through the resampling, if I resample 100 times, I can estimate the confidence interval of the slope. Because I get 100 estimates on the same numbers, but with no slope. And therefore, I can estimate the confidence interval. And this is a very simple way. Of course, when we didn't have the computers, it was very tedious, okay? But it was almost impossible. Yeah, by hand, yes. But with the computer, it's very easy. Actually, people did it like, you know, the well of the lottery. They were just, yeah, paper inside and then, yeah, by extraction. But this is very simple. And if you test it, you get precisely the same result that is given by the theory if the assumptions are met. But if you test it with a normal distribution, you start with normal data, you don't get the same result. Absolutely. And keep in mind this way of estimating uncertainty, which is, it's not always applicable, but in some cases, yes, it's applicable. And I mean, it's very powerful because it's also very easy. Okay, I think that with the confidence level we can close here, and this is what it's reported here. And basically here it's reported that least square estimation is usually applied in linear regression. It means that I minimize the sum of the squared residuals, and this is how R does it. When you compute LS fit, they minimize the sum of the squared residuals. And then it explains what is the confidence interval, what is the confidence level. Here the wording is more rigorous with respect to what I used during the lecture, but it's the same wording. So computation of the confidence interval is affected by this, not the same wording, the same concept, by the assumption on the errors, and in particular the assumption related to its probability distribution. If the residual are assumed to follow a normal distribution, and I didn't talk about correlation, but it's it's the same the same, it's another assumption that is done in linear regression, then we can compute the confidence interval, etc. Now, in order to relax a little bit, look at this graph here. This is, for us, a very important time series because it's the annual discharge, the annual maximum discharge of the Po River and Ponte Lagoscuro. And it's the daily discharge, it's not the instantaneous one. And it means that it's a bit lower because the instantaneous one lasts for 1 second. The daily discharge is the daily average and the daily river flow, and therefore it's a little bit lower. And so the question here is, given that the time series is quite long, here it includes about 100, less than 100, it's 91 years of data. Let's estimate the linear regression in order to see if there is a trend. But here, if you take the whole series, it shows that the max is a little bit increasing, a little bit. And so here, what is done is, by the way, the figure is generated in R, and it's, you see the power of animations. Anyway, what is done here is to estimate the linear regression over a window of 50 years. And it's quite a long window. And the result is a moving window. So first 50 years, and then from the second to the 51st, etc. You see the results that sometimes it's increasing, sometimes it's decreasing. And in blue when it's increasing, in the red when it's decreasing. So this means that there is indeed uncertainty, and I didn't try any of the estimations to compute the confidence interval, but still it means that you know, it's there is uncertainty. There is more blue than red here, but on the other hand, you see that in the final part of the period there is also some red. And in this case, if you want to estimate a confidence interval for the overall trend, you just have to shuffle the data. It's annual data. And here is the minimum. For the minimum, because you know the concept of the minimum is that it may decrease a long time before climate change. Actually, you see that again there is a lot of uncertainty. This is the annual minimum, and there was a huge minimum in 2003 and 2007. This gives an idea of the uncertainty of the estimation. And of course, remember, we are talking here of climate change impact and the challenge. We are talking about climate change impact, and this analysis of the Po River and Ponte Lagoscuro was precisely done because I was asked that question: is there climate change, and what is the impact of climate change over the Po River, which is very important for Italy. Remember that 60% of the gross domestic product of Italy is produced in the Po Valley. And the Po Valley is 70,000 of square kilometers. And it's a large part of Italy, but it's not the majority of Italy. I think the whole of Italy is like 220,000 square kilometers of extension. So it's about 1/3 of the valley, but it's producing more than half the gross domestic product because the resources are concentrated there, not for other reasons. There is a big flat plain, and therefore a lot of agriculture. Where there are mountains is more problematic, and there is a lot of water in the Po River Valley. Okay, so what is another way of estimating the climate change impact? So far, we talked about statistical measures. Okay, so it means that we look at the data and try to estimate if there is a change. There are other methods for doing that by statistics. And another one is, but I don't want to give more details, many details, the run theory, which is used for droughts. So basically, the linear trend is more used for the floods. The run theory is more used for floods. What is the run theory? The run theory is a way to measure cycles, because a drought is a cycle. So a drought is a long period. By definition, droughts are long. I mean, if you have a dry day, it's not a drought. If you have to define a drought, you need at least some 30 days of duration of dry. And therefore, it means that you start a cycle, no rainfall, and the cycle lasts for a long time. And particularly, we are interested also in multi-year droughts, which are phenomena that we know occurs, but we don't know what is the reason for that, and we don't know if under climate change the frequency of multi-year droughts is increased. Actually, it seems from the data that it's decreased, at least for the data in Italy. But also with respect to paleoclimatic reconstruction, it looks like the past one to couple of hundred years didn't show very long droughts. And so what is a way of estimating these cycles? Because it's not just one value. When we talk about a flood, it occurs in one day. It may last for a couple of weeks, but usually it's one day where you have a flow of the river. If it is an overflow, maybe also a breach in the levees, and then it's not related to climate. It's related to the stability of the levee, okay? But if you have an overflow of the levee, it occurs in one day, and you don't need, it's not a cycle. It's not, wouldn't be appropriate to use the run theory. But a drought, you have to estimate the frequency of cycles, and then what they use is run theory. Run theory is very simple. You take the average of the time series, and let's suppose that this one that you see here is annual rainfall in Bologna. Actually, annual rainfall in Bologna is a good case because it was analyzed with run theory. So what you do is compute the average, and then normalize the data by subtracting the average. Normalize, it's not standardize the data by subtracting the average. So you have the data fluctuating around zero. And then you fix two thresholds. Typically is plus 20, minus 20%. And then when you get rainfall that gets below the lower threshold, you start the run. And then the run may, you look at the next year. If rainfall is still below the threshold, like for instance, look here, rainfall below the threshold, you start the run. Next year, you are still below the threshold, you continue the run. Third year, you are still below the threshold, you continue the run. And then you get an year where rainfall is above the threshold. Should I interrupt the run or not? It depends. If the rainfall in this year is above the upper threshold, you interrupt the run. Otherwise, you continue it. So you see here, the run was continued. So this is a multi-year drought. In this case, you have a year that is above the threshold, you interrupt it. These are two independent drought events. And this one is just one, and is not a run. It's just one because the next year you got rainfall that is below the threshold, but then above the threshold. So this is not a run. These are, or let's say it's a run with a duration of 1 year. Okay. No, this is not a run actually. I don't understand why it is depicted in gray here. I think this is a mistake. I should remove this gray. This is a run with a duration of 1 year, and then it is interrupted. And this is a run with a duration of 2 years, and they are independent. This is a run with a duration of 1, 2, 3, 4, 5, 6, 7 years. This is a multi-year drought. And then you can define the duration of the run. And you can also define the severity. The severity usually is the cumulative deficit along the run. So cumulative deficit means you take rainfall of 1 year, and you take the difference with respect to the mean. Let's suppose that is -1. And then in the second year is minus 0.5. And then in the third is -2. So you get 1 plus 0.5 plus 2, it's 3.5. This is the severity. And then you can compute the intensity. The intensity is severity divided by duration. This is how droughts are usually quantified. And then how to detect climate change? Simply, you can count the number of droughts and see if there is an increase in the frequency along time. So the regression is against the number of cycles. Or you can compute a regression over a combination of number of droughts, their severity. Okay, so you can combine the number with the severity, meaning that you can associate to any drought, not just the number, but the severity. And therefore, when you compute the linear regression, you have a mix because you have a number of severities, not a number of droughts. So, but I don't want to give more details. And another question is, you may have is, but at the exam, what you're asking, and yeah, maybe at the exam I asked for a definition of the confidence interval, but remember that in the quiz, it's a closed answer question. So you have to choose among 5 alternatives, the correct one. You are not required to be very strict with the statistical terminology in repeating the definition. We are not really rigorous in that. Of course, you have to be able to identify the correct definition. Around theory, I may ask at the oral, like, can you please say what is around theory? And then you have to explain it. But again, not by writing, or it's just enough if you can describe what is around theory. Okay. Forget about estimation of long-term persistence because it's too detailed. And the long-term persistence is why it is described here. Because it's like correlation in the long time. And it is related to climate change because climate change sometimes, you know, it's difficult to distinguish the change from cycles. It's very problematic because you need a lot of data. If you look at trans theory, you understand you need a lot of data to estimate it. And these cycles are associated with correlation because when you get a cycle, it means correlation. If you try to estimate the correlation coefficient over a sinusoidal function, it's clearly very large because it means that there is a memory. The process remembers what happened in the past. And therefore, it's clear that instead of estimating the runs, the number of runs, you could estimate the memory correlation. And in particular, it is interesting, this phenomenon, which means that correlation lasts for a long time. Maybe that it is not very large correlation, but it's still correlation lasting for a lot of time, like 100 years. This means that once the climate takes a trajectory, it may come back to the previous situation, but it takes a long time to come back. And but let's forget about it, okay? Because I mean, it is too detailed for our purpose. What instead I would like to discuss with you is some alternative to statistics, because it's not the only mean that you may have to estimate the climate impact. Of course, statistics has the advantage that it gives you uncertainty of estimation, but there are also other methods, and the literature presents a lot of studies where there is a quantification of climate change and the impact of climate change without mentioning uncertainty. Why that? Because some people say, I am interested in change, no matter the statistical significance. So let's suppose that I have a small change, producing a small change such that is not statistically significant. So it may be something that also comes back in the future, is reversed in the future. But if this small change, which is not statistically significant, is almost no change, but if this small change produces the big damage, I am anyway interested in estimating the damage without caring about uncertainty. I just assume that this estimate is correct, and I want to see what is the result. So the literature discussed a lot about this. And why, actually? The literature discussed a lot. Because a lot of changes in climate that we see are not statistically significant indeed. So even the increasing temperature of global warming, there is a lot of debate. Some people say it's not statistically significant. And therefore the reaction is, okay, let's forget about statistical significance. Still, change that is important. Glaciers are retreating, and therefore I want to estimate the impact, no matter of statistical significance. And therefore there are alternative methods that are widely used, and an important alternative is the deductive estimation. Deductive means, as you know, that we start from the theory. So we make a model. It's like using the climate model. Okay, climate model uses theory of physics to estimate what happens in the future climate. And in most of the cases, they don't care about uncertainty. Here there is also a discussion of the fact that climate models, given that people know that climate models are uncertain, they often propose corrections. Again, another interesting story, long debates like, but if a model is wrong, you don't have to correct it. You just have to reject it. Because if it's wrong, it's wrong. And I mean, what is the meaning of making a model and then realizing that it's wrong and correct it? Sorry? Yes, because I mean, it's like an iterative process. So you make a model that is wrong, and you then introduce a correction, but the correction is still wrong. So you know, and also, you know, this correction is maybe correcting some of the features, but not everything. So this is called bias correction. Again, a long discussion in the literature, and what I'm mentioning it because I want you to know what is around climate change, because if you work on it, you will be mentioned for sure bias correction. And if you don't know what is, it's a bit of a problem, okay? But I don't want to study it. You see, it's very short. Okay, the discussion is very short. Just read it, and you will be not required at the exam to explain in detail what is, okay? Just to know that if I mention at the exam bias correction, you know what is, okay? And then let me instead give a bit of more details on a class of models which are widely used in hydrology, but now these models, rainfall runoff, are also included into climate models, into global climate models. Why? Because climate models were conceived to reproduce some climatic variables which didn't include the river runoff or runoff production. And but people realized that indeed this is an important variable, because of course the most of the impact of climate change over humanity is through water. And water, rainfall, yes, but not only rainfall, because actually for our purposes, we humans don't use water directly from rain. It's very rare, okay, in some of the cases, yes, but it's usually we use water from springs, from rivers, from lakes, from the sea, from groundwater. So it's important that we know not only the impact of rainfall, but also river flow. And therefore, climate scientists started to include also this estimate of river flow into climate models. Unfortunately, it is a bit of something that is still under development in global climate models, but it is very instead consolidated in hydrology. In hydrology, these models have already a history of, the first one was proposed almost 200 years ago. And then there are a lot of models available. And unfortunately, the connection between climate science and hydrology is very weak. It's very weak for many reasons. And therefore, this is a gap in our, let's say, effort to understand climate change and the impact. So I think it is extremely important to get some basic theory of this rainfall runoff models. And they are applied by following the principle of physics again, because it is the water cycle basically reduces to water flows in the liquid form or in terms of water vapor. But it is the description of a flow, and therefore you need physics. And you already know that physics, in the description of the dynamics of physical processes, the equations are conservation equations. And indeed, we also apply conservation of equation to describe the transformation of rainfall into runoff. We define runoff as the flow of water in general. When we say river flow, it's the flow of water into the river. The runoff can be over the hilltops, for instance, can be in whatever, it's water flow. And water flow, but not groundwater flow. The groundwater flow is explicitly called groundwater flow. Okay. So basically, this description, which applies the conservation equation, is usually done at a different spatial scale, different resolution with respect to climate models. Traditionally, river flow modeling refers to a spatial resolution that is given by the catchment. The catchment is the area that collects the rainfall that turns into river flow. Okay. There is a description of catchment somewhere, I think, but in any case, it's just enough for me that you know in qualitative terms. So the catchment is the portion of the land that collects the rainfall that turns into flow into a river. And this is usually our spatial resolution, which in some of the cases is lower than global climate models, because it may be like a very small catchment, like half of a square kilometer. In some of the cases, maybe a larger resolution, like the Po River Basin. Usually, the Po River flow is modeled at the spatial scale of the Po River catchment. There are plenty of models with different solutions, so we don't really want to study in detail the subject, but I just want to mention two models that are extremely important in order to precisely understand the impact of rainfall change into river flow, climate change, and in particular rainfall change into river flow. These two models are, first, the rational formula. Okay, this is a water cycle, but we don't need to. The rational formula is an essential model. Let me just explain it. Given by a very simple formula, this model was proposed in around the mid of the 19th century. So it has almost 200 years. And it's extremely smart, still applied today. And the rational formula basically says that the river flow is given by the product of three factors. The river flow here is Q. And let me go to the blackboard. So three factors. River flow is Q. And let's say river flow at a given time, okay? But let's omit the time here. And why? Because the rational formula was conceived to estimate the peak river flow. Rational formula, peak river flow. Okay. And so the peak river flow, of course, it occurs at a given time, but usually when we say peak river flow or a flood event, we omit the time because we are not interested in the time. Usually, we are interested just in the magnitude. So it's given by three factors. First of all, let me say the last one. It's the area of the catchment. You have this catchment with a river, okay, and the area of the catchment is A, okay, and this is the location where I want to estimate the river flow. Okay, so the area of the catchment, and then I have to put the rainfall intensity, I, and then a parameter, C, which is reduction factor. It is comprised, the C is in the interval 0, 1. And C takes into account water losses because what happens here? It rains over a catchment. It rains over a catchment with a certain intensity, and rain is measured in water depth, and the intensity of rain is determined by dividing the water depth by time. So usually when you listen to the TV, they describe a flood. Usually they say they got 200 millimeters of rain in 1 hour. It means that the intensity was 200 millimeters per hour. Or they may say, and you can say also per second, just divide 200 millimeters divided by 3,600 seconds in 1 hour. Okay. Or they may say they got like 400 millimeters in 1 day, which is half of the annual rainfall. So it means that the annual rainfall is 800 millimeters per year, and they got in 1 day after the annual rainfall. This usually happens when you get a big flood. Usually the amount of rain is about half of the annual rain. It depends on the size of the catchment, but indeed this is quite frequent. Okay, so it rains over the catchment with a given intensity. Okay, so let's suppose that you get like 1 millimeter of rain in 1 hour over the catchment. And then if you multiply the water depth by the area of the catchment, you get the rainfall volume that fell over the catchment. Of course, you have to take care of the units, okay? Because the rainfall usually is in millimeters and the area of the catchment is in square kilometers. So you have to be very careful. Yeah, you say yes, but when we propose exercises to the students, they always make mistakes in the unit conversion. Because, you know, rainfall is in millimeters per hour. But then we want the river flow in cubic meters per second, usually. So you have to make a lot of conversions, and it's very easy to make mistakes. The good thing is that when you make a mistake in unit conversion, usually it's a big mistake, so you realize it, okay? Because the number really explodes, and you realize it. But on the other hand, it becomes quite complicated when you have a lot of formula, acceleration of gravity, okay, meters divided by second square, rate, it's millimeters divided by hours, and you know it becomes a bit tricky. Okay, so basically, what you obtain if you multiply water depth by time times an area is a volume of water by time, and indeed the river flow is defined as a volume of water per time, per unit time, and therefore, basically, if you neglect C, you get here a very simple relationship. So the river flow is given by the volume of rainfall per time multiplied by the catchment area. This is very simple. It's a pure mass balance. Mass balance. Okay, and then there is C. C takes into account the fact that you have some rainfall losses, evaporation, infiltration in the underground, and therefore C is between 0 and 1. And this formula, which is very smart, is widely applied in engineering, because if you want to be very conservative, you take C equal 1, and you get an estimate of the river flow very readily, and just without any pocket calculator. And in fact, it was introduced 400 years ago without any PC. You just think, okay, they got 200 millimeters of rain for 1 day, and then the catchment area is 10 square kilometers, so it's very easy to make the computation. And also by mind, I mean, without any help of any computing facility. And of course, I mean, here there is something that is uncertain, not just in the definition of the catchment area. I mean, there is uncertainty, but not very relevant. There is a lot of uncertainty in the definition of C, because, you know, if C is 0.5, you get a kind of estimate. If C is 1, you get twice the estimate. So there is a lot of uncertainty. But on the other hand, we have some engineering ideas for estimating it. And then there is the estimation of the rainfall. The rainfall usually may be given by climate models, so it's okay. But the big question here is not just the estimation, but what is the reference rainfall that I should take? Like, if I am interested in estimating the peak river flow with a probability of 1% of exceedance, what is the corresponding estimate of rainfall? So first of all, we assume that they have the same probability. So we say, okay, the 1% probability of exceedance river flow is given by the 1% probability of exceedance rainfall. This is quite an easy assumption. But on the other hand, okay, let's suppose that the rainfall on after precipitation is linear. Actually, it's not linear. If you make this assumption that the probability are the same, it means that it's linear. Okay, but rainfall is also expressed intensity, as we said, for a duration. So should I take the hourly rainfall with 1% probability of exceedance, or the daily rainfall of the monthly rainfall? So what kind of duration rainfall, remember, is characterized by the probability of exceedance, rainfall event, and the duration. This is why the TV says they got 400 millimeters in 1 hour, because they have to specify the duration. Because if it is 100 millimeters in 1 day, it's less concerning, it's less relevant. So what is the duration? And here there is an interesting thing that you can read on the lecture. It can be proved in hydrology under certain assumptions that the duration that is most concerning rainfall, duration D, what is the most concerning? So if I want to estimate the peak flow for this catchment, what is the duration of the rainfall that I have to cost? The duration is equivalent to the time taken by the drop of water that reaches the furthest point of the catchment, in the point that is most far away, to reach with what kind of to reach the outlet. So this is a duration T. So how long does it take to the drop? Time of concentration, yes. It's called time of concentration. What is the duration that takes a drop from the point that is in the far location with respect to the outlet to reach the outlet? Oh, this is something that is not physically measurable. It's something that is concerning, can be estimated. So I can tell you that for the Porian is about 10 days. I can tell you that if you take the rivers that flooded in the Romagna region 2 years ago, it's about 6 hours, 7 hours. And this means that you have to look for the rainfall with the same duration. And therefore, what is the interesting implication which we always want to stress? If you have a change in rainfall, not necessarily implies a change in flood risk. If you have a change in hourly rainfall, hourly peak rainfall for the Po River, it doesn't matter. If you get even twice hourly rainfall for the Po River, but you get same 10 days rainfall, Po River doesn't care about the change in the hourly rainfall because it takes so long to reach to the outlet that it gets smoothed out. It takes 10 days. So 1 hour, just 1 hour of heavy rainfall in the Po River, no problem if the next hour is dry. If you get instead for the Po River 1 hour wet rainfall, and then 1 hour, 1 hour, 1 hour, 1 hour for 10 days, then of course the Po River gets into a crisis because if you make an elementary consideration, it means that after 10 days, there is no more smoothing. Every drop over the catchment gets into the river outlet. This is the rationale. And this is indeed very interesting to understand the impact of climate change. And this brings us to say what I just said. So the rivers in the Romagna region, why they flooded? Because indeed what we see after climate change, after global warming, is a change in short-term rainfall. In the rainfall that lasts for few hours, from few minutes to few hours. We don't see a change, a so dramatic change in weekly rainfall. And this is why, after global warming, the Po River is not flooding, but the small rivers are flooding. So you understand the importance of a very simple relationship like this in conveying a concept that is indeed extremely relevant.
A brief question. The runoff coefficient, the value in particular, what does it depend if it's 0, 0.5, 0.1?
It depends on the water losses that you have on the catchments. But the good thing here is that when you get a flood, usually the runoff coefficient is very close to 1. When instead you have low flows, so the runoff coefficient is close to 0. And you easily understand why, because during a flood it rains, and so you have reduced evaporation. And during a flood you have a very heavy rainfall, and infiltration in the ground is very low because it doesn't have time to, I mean, the ground has a limited storage. When instead you have a low flow, it means that it rains rarely, it rains less, and therefore the most of the rain is lost for evaporation and infiltration into the ground. So basically, for floods, we say it's about close to 1. The question becomes more problematic if you want the annual runoff coefficient. The annual runoff coefficient is usually estimated by looking at data. So if you look at the annals of the Hydrological Service, the books that keep the records of river flow and rainfall, they suggest for any river station, they suggest a value of the runoff coefficient, long-term one. And so this is the way it is estimated. But this is what makes this formula good for, empirical applications, but not very good for very quantitative design projects, because there is a lot of uncertainty in the definition of C. I just want to say one thing before I close. Here, you may say, what is energy balance here? Energy balance is not needed because this is a formula that doesn't describe flow, it describes only value, peak. So you don't need energy balance here. It's just mass balance. If instead I want to describe the flow and the progress of Q over time, which means the flow, of course, I need an energy balance to describe the movement of water. Okay, let's stop here. So let's meet again at 2:05, given that I took some more time.
One step that will show us that during these classes can be present during our discussion.
For this exam, no. And it's usually we don't make any exercise during the oral examination. And therefore, I mean, we prefer not, because the oral examination is very short. You can describe it, but not take the PC and present it.
Or the concept that you explained to us when you explain about that.
Yeah, you can describe by words. Okay.
And can you also provide us a short list about the questions?
Yes, I'm planning for the next week. I make a summary.
That's it. Okay, thank you.
No problem. During the last class, I will make a recap of what we started and
For the next class, during morning of short students, we cannot attend the class because we have an exam.
Yeah.
But during the afternoon, we can be present.
Okay, very good. Perfect.
Prof,
Yeah.
regarding what the colleague was asking, I didn't understand properly, maybe because it was not so loudly, but I was curious also in this regard. The answer that professor provided, saying that the student should give a description, but it doesn't need to take the laptop. Is it regarding the laboratory part?
No, it is regarding this exam. They asked to whether for this exam you may present a code. And for the lab, yes, you can present a code. But also for the lab, next week I will describe how how the exam takes place in detail. Okay.
Okay, thank you.
See you later.
Excuse me, I have a question regarding the exam.
Yes.
So the question is, so we, for example, we programmed with R some things and all that stuff. Is that also part of the exam? Because I think it's quite hard to ask
Yes.
for.
No, it's not part of the exam. And as I mentioned earlier, the exam is through a quiz, and the quiz, of course, there is no question on coding. And also the oral part, you are not required to make any computational exercise through the personal computer. So the other parts served only for the purpose of providing examples, but it's not part of it.
Okay, so it's more about the understanding of the things we're discussing.
Yes, yes,
Okay.
that's
Okay.
true. Okay,
I wanted to be sure. Yeah.
okay, thank you very much.
Thank you.
Okay, perfect. Now, 1 second, I need to, very good. Okay. For some reason, the recording has not been interrupted during the break, so I will need to remove the gap by editing the video. So maybe that it takes to me, but I think tomorrow should be online. But I'm not really sure. Maybe Friday, because it depends on the timing of the rendering. Okay, so let me just check. I want to make sure. Yes, the registration is still ongoing. Let me share the screen. Okay, good. Firefox. So we were talking about, again, inductive and deductive estimation. We closed with the discussion on the rational formula. Let me now show you one thing. The rational formula is about rainfall runoff modeling, and it's here. The next one would be another model that is used in rainfall runoff, which is the linear reservoir, and we skip it. Okay, and maybe next week, if I have some time, maybe that we can get back here. But for now, we skip it. So don't study it. It's not also part of your exam. Okay, so what I instead, sorry, I would like to do today, because this lecture after the linear reservoir is essentially finished. And yeah, also the nonlinear reservoir. And there is also a section on estimation of future forcing, but it's 2 paragraphs, and this one, you can skip it. Okay, so what I would like to start in the afternoon instead is the next one is the lecture on decision theory. Let me just take the PowerPoint, and I'll then make a short introduction. Okay. Okay, good. So let me make a short introduction about this. Decision theory is something that is related to engineering for obvious reasons, because sometimes we have to decide among different alternatives. We have to decide which solution is the best one. And this is particularly demanding in the presence of change, because in the presence of change, we realize that the climate in the future will not be the same as in the past, and therefore the selection of the most appropriate solution is complicated by the presence of uncertainty, because as we repeated many times, even the present climate is difficult to assess with the limited uncertainty, but when we talk about the future climate, indeed uncertainty is increasing. And therefore, the selection of the most appropriate solution is indeed more complicated because we have to take uncertainty into account. Uncertainty means that when you predict the benefit of a given solution, a benefit that it will give in the future, actually, when it turns out to reality, the benefit may be lower or may be higher than expected. Usually in engineering, we use cost-benefit analysis to make decisions. So if we have different alternatives, we usually try to estimate the cost and the benefit of each of them in the long term, in the future, of course. So you need to apply discount rates, the interest, etc. And then we select the solution that provides the most relevant benefit, the higher benefit. In the presence of uncertainty, this becomes a bit complicated. Why? It may look like it is more or less the same problem because you have a best estimate, and of course you can make the cost-benefit analysis by referring to the best estimate. On the other hand, as I mentioned, uncertainty means that the benefit may be higher or lower than expected. And you are particularly concerned by, of course, the benefit being lower than expected. And therefore, when you evaluate alternatives, optimality, meaning the higher benefit, with respect to the best estimate, may become not really the most preferable solution because, for instance, you may want also to make sure that whatever the future is, you don't have a significant damage. And therefore, a solution that makes sure that whatever the future is, you get anyway a benefit that is not the best one necessarily, but it's not the worst one, the other end, maybe an alternative that is preferable because it presents the advantage of limiting the damage. So you understand that the decision becomes more complicated, and also the selection of the best alternative depends on the stakeholder, on the type of the benefit that the stakeholder receives, and it also depends on the attitude of the stakeholder. So is the stakeholder willing to take the risk? Is the stakeholder willing to pay to minimize the risk? Or instead, is the stakeholder a person who is willing to take risks in front of the perspective of a high gain? So it becomes something that is very subjective at the end of the story. And when we have multiple stakeholders, there is also the problem of trying to reach a compromise among all of them. And also the procedure, when you have multiple stakeholders, needs to be transparent because if you want to reach a compromise, it's important to gain the trust of the stakeholders. And if your procedure for evaluating cost and benefit of each alternative is not transparent, it becomes more problematic to get the trust of the stakeholders. So on the one hand, you have a complicated problem for the presence of uncertainty, for the presence of many stakeholders, which, as I said, have different perspectives. On the other hand, in view of this complex problem, you have to adopt a not necessarily simpler, but transparent decision procedure. So your decision making must be understandable. Transparent means also understandable. So you have a complex problem, but you cannot just show a computer code and press enter, running the computer and showing the final results. You have to be understood by the people. So it becomes really an interesting problem, and this is why the subject of decision theory has had a huge development in the past 50 years. When sustainability and climate change became an issue, And sustainability became an issue at the beginning of the 70s, and climate change became an issue about 25 years ago. So after the realization that these two problems became issues, then decision theory had a big development, a big revolution, because, as I said, there was the necessity to solve complex problems with a transparent procedure. Actually, decision-making is as old as humanity. It is only the recent development that was really revolutionary with respect to what we were used to do in the past. I said decision theory is as old as humanity because humans indeed are used individually in the everyday life to take decisions in the face of uncertainty. If you think at your everyday life, every day you have to take decisions. Some of them are important, others are less important. And for some of them, you have anyway a huge uncertainty, others have a less relevant uncertainty. For instance, when you have to decide whether to take the umbrella or not to go out, or whether you have to decide whether or not to take a job that is being offered to you. So the job is an important decision, and there is uncertainty because even if they show you the call for application shows to you all the benefits that are attainable and all the costs, still there is uncertainty because anyway you have to get into a new environment, a new people, and therefore you have to take a decision whether it's worth taking the job without an alternative that you may have. In some of the cases, there are no alternatives and there is no decision problem. But in many cases, we have indeed alternatives which we have to evaluate. And individually, as I said, we are quite used to do that. Still, decisions that individuals take can be very different. To the same problem and same alternatives, different people can take different choices. It depends, as I said, on the willingness to take risk, on your capability, on the capability of the individual to evaluate uncertainty. And so a person that is very skilled in considering uncertainty may be more keen to take a different decision with respect to a person who doesn't care about uncertainty. There are some people indeed who don't care about uncertainty because they think uncertainty is indeed a concern. It's an additional concern. So some people say, okay, I take the best decision and I don't care about uncertainty. Other people are very rational. So they evaluate analytically every downside, any consequence of a decision. So there are some people that even when they have to take a different road to reach a destination, they evaluate everything, the cost of the fuel and the cost of the highway, if there is any highway, the timing, the risk of an accident with the car and the consumption of the tires. There are other people who just decide by their inclination. So they say, okay, they see two roads and say, oh, this looks more attractive to me. And they take that road and without thinking of the consequences. This is because the individuals are used indeed to deal with uncertainty with individual approaches. When you come to putting people together, you understand what can be the complication and when seeking compromise. So what are examples of ancient problems that were solved through decision theory? Here you can see a picture of the Nilometer along the Nile River. And it is a staff through which people went to put a sign every year, and the Egyptians, a sign every year of the highest flow of the River Nile. So basically this staff is connected to the river. There was a pipe connecting the river bed with the staff. Water was going up. At the end of the year, they went down along the stair and signed the highest point reached by the Nile during the year. And then they, basing on recording of the Nile that they took for more than 600 years, they decided, basing on the record that they took for the previous year, what kind of cultivation they would adopt for the next year. Because, fertilization was depending on the floods of the Nile River. So they took a lot of decisions. based on this kind of information. This is the first example of a decision problem to be taken under uncertainty, which was solved by getting information about the Nile River level with respect to the previous year. And there could be several examples. And for instance, during wars, indeed, the militaries were used, and the very good strategic generals, they were used to evaluate strategically what kind of tactic they could adopt for the next war, for the next battle, and in the presence of uncertainty. And some of them had very defined decision processes based on several types of information that they could get. Of course, there was uncertainty. There was no need to reach a compromise because you know that under military emergency, one of the strict rules is that there is one person that decides, or a group of a very small group of persons who decide, and then there is no question of criticism with respect to the decision. The rule is that the decision, once taken, must be followed. Recently, we had, as I said, after the advent of personal computers, we had an improvement of these systems. And the first improvement was precisely the cost-benefit analysis in a mathematically rigorous way, which is based on the valuation, usually in monetary units, of the cost of each decision and the benefits that in the long term the decision will bring. And for sure, in your bachelor, you had some examples of cost-benefit analysis as a first approach to decision theory. Cost-benefit analysis may have considered, in your case, uncertainty. Usually, it was, especially in the past, resolved when they didn't have large computational resources. It was resolved through the best estimation of the best estimate. So cost-benefit were evaluated for the best best estimate. Okay, so if, for instance, I have a prediction of peak river flow in the future or CO2 concentration in the future, and it is subjected to uncertainty, I take the best estimate and that's it, and I make my computation with the best estimate. This is still widely used. For instance, the future emission scenarios, they basically are represented by one line, and this one line provides our best estimate. Usually we don't take into account uncertainty of each of them. We account in some ways for uncertainty, partially for uncertainty, by considering different emission scenarios. But actually, very often people tend to use the most skeptical one, the worst one. So they work with the worst, usually worst scenario, and take it as best estimate. Using the worst scenario is, in this case, it is not a good example, but let's say that when you have an estimate of, for instance, future climate, you can decide, instead of relying on the best estimate, which usually is based on the average of your uncertain prediction, you could take the worst case. So if you have an estimate of uncertainty, you take the worst case, so the estimate that produces the higher costs, and then you make your cost-benefit analysis with respect to the worst case scenario. And this is what is adopted with emissions. So in the emissions, you take the worst case scenario, and this is a way to account for uncertainty. But for the worst case scenario, still it's a best estimate. Anyway, referring to the worst case, what is the problem? The problem is that the worst case is not the most probable. It's the one that has a very low probability. So the reality will be different. And therefore, the reality will be different means that probably the cost associated to what will happen in the future will be less than what is predicted, and the benefit may be anyway less than that. And therefore, I mean, not necessarily the worst case scenario is the scenario that gives the highest benefit. Because by taking the worst case, you get a decision that basically may lead, for example, to heightening a levy, and therefore the worst case implies a high cost, and the benefit that will be taken consequently will be lower. This problem of selecting an alternative is also similar to the problem of parameterization of a model. I left the rational formula on the blackboard because it's an exam. So we discussed about what is the value of C to be taken. And adopting the C value is a decision, which I said we usually resolve it if we want to be conservative. We resolve it by adopting C equal 1. This is a typical worst case scenario. On the other hand, keep in mind that if you make a design project with respect to that estimate of river flow, it requires a lot of resources because the river flow is high. And at the end of the story, maybe that your project is not realized because it is too costly. So this is an example that clarifies, on the one hand, the limitation of the worst case scenario. It's not a simple solution. This is what it's usually adopted with future climate scenario. People, as I said, takes the most pessimistic emission scenario, and then we end up with the predictions that are excessively conservative, and the result is that we don't do anything. So the worst case, the moral of the story, take-home message, not necessarily is a good solution, because otherwise the decision problem would be relatively simple. Second thing, this example of the rational formula tells us that even parameterizing a model is a decision problem. It's a different kind of decision problem with respect to deciding whether or not we need to build a dam, but it is still a decision problem. And this gives to you the idea of the fact that the decision is a process that is multifaceted. It can assume different connotations. And this explains why there are several approaches, several models that are included in the domain of decision theory, and several sub-theories of decision. With regard to model parameterization, and I go back to the web page 1 second because I have a link to follow. With regard to model parameterization, an interesting example is to look at the story of model parameterization, because it gives some ideas of how the problem can be solved. And let me see, linear. Okay, I was looking for this link here. So first of all, at the beginning of the history of models, people estimated the parameters with a trial and error procedure. So it was typically a problem that was solved by attempting different values of parameters, and the best solution was identified according to an objective function. And typically for models, an objective function is a goodness for fit measures, goodness of fit measure, like least squares. So I decide to estimate a model by minimizing the errors, in particular by minimizing the sum of the squared errors. And therefore, with trial and error, people try to check what was the best solution. This is not a cost-benefit analysis. It's an optimization with respect to an objective function that is not related to a cost or a benefit. The objective function in this case, the benefit can be an objective function, but in this case, the objective function is model reliability. So it's an optimization problem. Optimization means finding the best solution, and in particular, the best parameter value with respect to a target. And the target in this case is not a cost-benefit analysis. This marks also the difference between model parameter estimation and maximizing the benefit. For model parameter estimation, the problem is not to maximize the benefit. The problem is finding the best model. And therefore, the target is the reliability of the model. And as I said, people were going by trial and error. Trial and error means that you just throw by chance a parameter value, like for C, you know that the range is 0, 1. You extract by chance a value between 0 and 1, and you compute the peak flow with that value, and you compare the peak flow with some term of comparison. Like, for instance, the Egyptians had the Nilometer, they had data of river level. You can, if you obtain an estimate, if they wanted to estimate the rational formula on the Nile River, they couldn't because the rational formula didn't exist. But if they could estimate, if they had the rational formula, they could plug in every year. They could measure rainfall. Actually, it was not a usual practice to measure rainfall in the past. Also, it was not a usual practice to measure the river level. These are variables that are very easy to measure. Only the Egyptians had this idea of measuring the river level, but they didn't measure rainfall. But let's suppose that they had the rational formula and they had also a measure of rainfall. They could try to estimate it because they knew the area, or they didn't also knew the area, but they could get an estimate of the area of the Nile River, and they could just multiply rainfall by the area of the Nile River, and they could plug in by chance a value of C, get an estimate of the river flow, convert the river flow into river level. This is relatively easy. And then they could compare the results. And if the results of the comparison were not good, they could try another C until they got the right value. This is trial and error. And this was usually done in the past. By the way, the Egyptians couldn't do that, not only because they didn't know the rational formula, not only because they didn't measure rainfall, but also because they didn't know that river flow comes from rainfall. This was an understanding that people gained only around after the Middle Age, around 1600. And you may think something like how that could be, that people didn't realize that the river flow comes from rainfall. The Nile River is a good example. They didn't know that because they were flooded in some years where they didn't get any rainfall, because the rainfall was coming from Ethiopia or from Sudan. So the Egyptians, there was no connection at that time. And therefore, they couldn't know that it rained a lot in Sudan and in Ethiopia. They got flooded without any rain. And therefore, the assumptions that people made up to 1600, more or less, was that the water of rivers was coming from the underground, like an eruption, like a volcanic eruption. They thought something like that. And if you think of it, it's not so bizarre, because if they saw volcanoes, and they could also think of assimilating the river flow to the flow of, I don't know how to say in English, from the flow from volcanoes. I don't know how to say lava, the name in English of the flows from volcanoes, but I think you got it. So they couldn't apply it, but still the message is clear, meaning that trial and error is such a kind of procedure. After the advent of personal computers, people thought that trial and error could be done automatically. And they did that. Like, okay, let's by chance generate a value of 4C and let's try it automatically. But then when they had this opportunity, they thought that it was very nice and they tried to also make the models more complicated, more complex, with more parameters, because they had the personal computer, the facility for computation, and therefore the models increased of complexity. Now we have machine learning. Machine learning has really a lot of parameters, like 300, 400, and therefore they realized what? That the trial and error, when you have to try different combinations, because you cannot try one by one. When you have 300 parameters, you have to try a combination of 300 parameters. Basically, the trial and error took ages. Like 1 month, the PC was running and trying different combinations. And therefore, they had the idea of devising guided search procedures. This means not just trial and error. It's trial and error plus guided search. So the procedure should learn from each error, and the next value is not selected by chance. The next combination is not selected by chance, is selected with a guided search. And the first of these solution was linear programming. Linear programming was widely applied in order to put this kind of guided search into practice. And you see here, linear programming, also called linear optimization, is a method to achieve the best outcome, such as maximum profit or lowest cost, in a mathematical model whose requirements and objectives are represented by linear relationships. Okay. And it was an important step forward in water resources management, and therefore in the estimation of climate impacts. There was a massive use of linear programming starting from basically the 70s of the past centuries, when they had indeed access to computational facilities. And this allowed to improve a lot the modeling process, improved a lot model performances, and it was indeed an active field of research, then evolved in several different algorithms, which are those that you now find in Excel, in R, in Python. So when I estimate the linear regression, R search the best estimate through minimization of the sum of squares. And this minimization is not done by trial and error, pure trial and error. It's done through a guided search. And this is why it's so rapid. And you could also make it by pure trial and error. You can try it, but you would realize that the timing is much longer. And so this is the first
Professor,
example. Yeah. Yes.
This linear guidance key that professor is mentioning, is it the same that the brands of casinos and this
You mean game theory? You mean
Professor?
do you mean game theory?
This linear programming that professor is discussing now, I'm asking whether is it the same, because on those big companies that work with odds, they keep on narrowing the odds according to the number of games that the players, the more the players play, they get the information, and they use an algorithm that learns from those experiences, so that it makes more difficult for them to win for the next time and the company earns better? Is it this linear programming or is something else?
There are several algorithms for optimization. I doubt that today in industrial problems, they use still linear programming because, as I said, there has been a huge development. And but the most important thing, so I can't say it's linear programming what you mean, but the most important thing, take into account that sometimes there is also proliferation of heuristic methods for taking decisions that give the illusion that you can gain the capability of predicting something that is completely completely random, which is of course not true. So you mentioned the casino. The casino, which is a process that is completely random when you turn the roulette. But of course, there are people that, basing on the lack of appearance of a number for several different trials, they adopt heuristic models to compute the probability that the next trial, the number will come out. And this is, of course, wrong, meaning that when you turn the roulette wheel, it's always a random process, but still there is a proliferation of algorithms of people who are a bit superstitious, like they believe that luck can be predicted, and therefore they use them, but they are not scientifically based. So I just wanted to make sure that you don't make, you understand the difference between something that is purely heuristic, and therefore it's not theoretically based, and I have no way to check the quality of the prediction. Distinguish this kind of procedures with respect to procedures that instead are more theoretically based. So I'm not really sure if the example that you made is an example of a heuristic prediction. For sure, anyway, to reply to your question, in the industrial environment where they are used to use decision theory every day, they don't use linear programming anymore. Linear programming is very simple. This is the nice thing. But today we have computers that allow to use different methods, which I am now describing. Okay, so linear programming in its classical formulation doesn't take uncertainty into account. So basically, with linear programming, you estimate, basing, for instance, on a measure of rainfall in the rational formula, you can estimate with linear programming the best value of C, basing on the comparison of the result from the rational formula with an observed value. So with linear programming, you can do that. But usually, we don't account for uncertainty in the measured rainfall or uncertainty in the river flow that is used as a term for comparison. So there is no consideration normally in linear programming about uncertainty, unless people decide to make a different optimization problem with different input data. And in this way, they can account for uncertainty, but it's still an empirical method. So what really we need is a support to the decision problem when the information that we have is uncertain. And sometimes people say that they try to classify uncertainty in different categories. Usually I don't like this kind of classification because uncertainty for me is just a unique category. But some people say, in climate science, we have deep uncertainty. What does it mean, deep? As far as I know, there is not a rigorous definition for deep uncertainty. It's an uncertainty that is supposed to be large. So, especially when uncertainty is large, the message is we need to take into account explicitly with a theoretically based method. And therefore, about 50 years ago, there was the development of what is called robust optimization. And it's a first method to take decision in the presence of uncertainty. It's a very active field of research today. What does robustness mean? we already introduced robustness. Robustness means that a solution is not necessarily the solution that gives the highest reward, but it's a solution that whatever the future will be, doesn't give a big damage. So basically, it could be, instead of the search of the max benefit, it could be a research of the max of the lowest benefit. And indeed, it is called, this method is called min-max. So the max of the mean. I don't look for the max benefit, but in the presence of uncertainty, where I could have several different benefits, ranging from low benefit to high benefit, for the same solution in the presence of uncertainty, I may have several different benefits, ranging from a minimum and a maximum. So the idea could be, I look for the solution that gives to me the max of the minimum benefit. So I'm not looking for the solution that gives to me the max of the maximum, but the solution that gives to me the max of the minimum. It's called the min-max method. If you Google min-max, you find a lot of entries. This is for sure a good idea, but you understand that if you are working in an industrial environment where maximization of the profit is the target, and it's a very fair target, of course, this is not, I mean, people usually are not happy with this solution because it means that you give up reaching the max reward possible. It's you look for the minimization of the damage, and this turns out in a limitation of the development. And in the industrial development, this is a huge problem because in the industrial development, you have you work for the development, for innovation. You work for innovative solutions, and of course, with the min-max, you give up to adopting the solution which gives the max reward. So people try to understand how to find the best solution, and then several methods came forward. And now let me just go back to the PowerPoint. Okay, we already discussed these considerations. And of course, I mean, if you want to consider uncertainty, you need probability. So probability was identified as a powerful support decision theory. On the other hand, as I already mentioned to you, probability is not the only way, the only possible solution for dealing with uncertainty. You may have heard about fuzzy logic theory. Indeed, fuzzy logic is an alternative to probability. And, or you may have heard about the possibility theory, veridicity theory. So instead of looking if something is probable or not, you look for if something is possible or not. And so there are several branches, but indeed, probability has a lot of theoretical fundament, and therefore it's something that is very widely applied into decision theory. Okay, I think we already discussed this. So let's try now to start discussing some of the methods. And the discussion that I will propose to you, we will discuss about 4 or 5 methods for taking decision in the presence of uncertainty. And these methods, first of all, they refer all to a climate adaptation problem. So I selected them. So let's forget about linear optimization. Let's forget about genetic algorithms, other algorithms for optimization that are purely dedicated to optimization of model parameters. They can be used into a problem of estimating, finding the best solution to adapt to climate change, because we need models. So I may have also an optimization problem for a model to solve, but let's assume that now our problem is more targeted, more specific. I have to adapt to climate change, and I need to identify the best solution. So, for instance, let's suppose that climate change presupposes for the future an increase of the temperature. So my problem is, should I invest resources in air conditioning into the buildings, or should I invest resources in greening the cities? And by taking into account that very often we don't have enough money for doing everything, because of course, if we have enough resources, we green the cities and we put air conditioning and that's it. But we don't have enough resources, and therefore we have to think about, okay, what is the benefit that I can take from air conditioning? The benefit is clear. Inside the houses, you have a very good temperature, but on the other hand, outside, it's very hot. And it's even hotter than without air conditioning, because in the cities, the air conditioning increases the temperature in the street. So the problem is that when people from the inside of homes goes out, then they get sick. Like it happens to me when I take the train and I leave my home, which is quite cool during the summer. And then outside is hot. And then I get into the train, is completely frozen. And then I take the motorbike to go to the office. I am sweated, and then it's hot. And then into the office, it's again frozen. So this is a problem. And also there is the cost of air conditioning. And do we have enough energy resources also to give the power to the air conditioner? On the other hand, if you green the city, of course, the mitigation effect is, the mitigation of the temperature is less effective, because you don't bring the temperature into a city to 20 degrees, but still you may bring the temperature from 35 degrees to 30 degrees, which may be fine. And on the other hand, there is to say that the result is affected by more uncertainty, because, you know, who knows what kind of trees, and who knows what is the effect on the temperature. With air conditioning, you are quite sure. I mean, if you take an air conditioner and you give power until you get the desired temperature. So this is the kind of decision we refer to, or more with a wider perspective. Should I try to mitigate climate change, or should I adapt to it? So should I invest money in reducing the emissions, or should I just forget about it because it's too costly, cannot be done all over the world, because in India and Africa it's difficult to reduce the emissions? So should I give back to it, give up to it and adapt, or given that I don't have enough resources to minimize emission and also adapt, should I give priority to mitigation, forgetting about adaptation? This is a big question today at the global level. And you know also the implications with Trump that decided to give up with mitigation of the emissions, or at least lower the priority, and because he thinks that is too costly, the time scale is too long. By the way, it's reasonable to say that. It's a reasonable concern indeed. And it's reasonable to be concerned by the European attempt to reach decarbonization by 2050. It's not an easy target. So basically, this is the kind of decision we refer to. So let's talk about robust optimization. What is robust optimization? So basically, the identified solution, look at the second bulleted point, will always guarantee the optimal functioning of the system, even in the worst of the several scenarios that can materialize. So the system will anyway function, okay? And the most classical example is given by a problem where a single objective function is to be optimized under uncertain constraints. So I have an objective function to be estimated, to be minimized, and maybe that, like in the rational formula, the river flow is measured with uncertainty. Or, for instance, here, water resources availability for a given future may not be known for sure. It's not known for sure, by the way. I have a range, the confidence interval, for a given confidence level, and therefore I look for the optimum by referring to different scenarios of water availability, and I basically don't select the solution that gives to me the best optimum, but there is some criteria for robustness, not necessarily min-max, and it could be something more elaborated. This is robust optimization. And before turning to robust decision making, let me just go to the web pages, because there is something that I need to robust optimization, the link. There is a Wikipedia page, and there is an example here. Let me see, because yesterday I put a link here, which, okay, see the example that is presented here, okay? And this is the example. So this is a linear programming problem. So let's suppose that you have an objective function. You see that it's linear, 3x plus 2y, and I want to search for the max, okay? So let's suppose that this is a benefit, for instance, the result from a cost-benefit analysis, but I have constraints. And the constraints are x, y are greater than 0. And the most important thing is this constraint, cx plus dy must be lower or at least equal to 10. And for any couple CD, which pertains to a subset of R squared. So the C and D are two numbers, two numbers variables. And therefore the constraint is subjected to uncertainty, because C and D are not known for sure. And indeed, this is a robust optimization problem, because the constraint must be satisfied for any C and D value. So, for instance, when I talk about water resource availability in the future, the constraint can be that water resource availability is in the range 50, 60, but you don't know what is the range. And therefore, this is a typical robust optimization in which you could basically the constraint must be satisfied by the worst CD. This makes it robust. Okay. And of course, this is just an example, but we could give several different examples. And there is the solution to this. And if the parameter space is finite here, then this robust optimization is itself a linear programming problem, and which is not solved here, but can be solved with the linear programming. Usually the classical linear programming is you have C and D that are fixed. If they are uncertain and you still have to satisfy a constraint, you have to look for, and the constraint has to be always satisfied. It becomes a robust optimization problem, because you have to look for the worst condition given the possible values of C and D. Okay. And this is a first method, which, I mean, we don't go into the details. For some of the methods, we will go into the details, but this is, we don't go into the details. And let's also say that sometimes the constraint is not so strict. You may wish that the constraint is satisfied, but you may accept 20% of the risk. So the constraint can be expressed into through a probability. But the take-home message, what you have to remember about robust decision making is just what is the difference with respect to optimization. Optimization, you look for the optimum, And in robust decision making, you don't necessarily look for the optimum, but you look for a robust solution. Robust means that you basically set a target on the lowest benefit that you may get. So you have a target in saying, okay, I want to maximize the benefit, but I also set a target, a constraint on the lowest benefit that I want to get. Yeah, and the constraint can be fixed, like in the example, fixed meaning that in the example that I gave earlier, like I want to find the maximum benefit with the constraint that in any case, I never get less than 20, okay? This is a fixed constraint, like, okay, I want to seek for the maximum, which is maybe 100, but I put a constraint. And the constraint is that whatever it happens, at least I get 20. So I reject a solution that could give 0. Magari yes, Italia. Maybe the solution gives the highest benefit, but it may happen that it gives 0. I reject it. So it's not searching for the optimum, for the max benefit. It's searching the max under a constraint on the minimum. This is robustness. And the constraint, you can express it in terms of probability. This is the last thing that I said. Like, okay, let's say I don't want to get less than 20 with a probability of 95%. So I really want that less than 20 is something very limited. It's still a robust optimization. And this is just a take-home message that you need to take. It's not anything more from this method. I could solve the example that I made earlier, but let's forget about it. I could show you that with linear programming is quite easy. And by the way, it's quite easy if you go with trial and error, 2 parameters, and you can make in R very easily 1 million may be too much, but 10,000 attempts, and then you select the best one that satisfies the constraint. Is quite easy. This is robust decision making. Okay, and let me close this. Okay, now basically, yes. Okay. So basically, what are the steps for applying robust decision making? First, you have to identify the future scenarios, system models, and metrics to evaluate success, like in any decision problem. Okay, in any decision problem related to climate, we normally have to identify our expectation for the future, maybe in terms of probabilities, and then the models that you want to apply and the metrics. And then you have to evaluate the system performances, meaning that you apply your models in order to compute the desired variables and you compute your benefit. And then you have to make vulnerability assessment. Vulnerability assessment means what can make this solution not working. So for any solution, you have to identify all the shortcomings. So for what reason it could give a benefit of 0, and then adaptation options to address these vulnerabilities. And then adaptation options means you select the best solution according to your decision method. And then there is risk management, which is not compulsory, but maybe that if you see that the solutions entail a relevant risk, you can also set up a contingency plan. Like, okay, let's suppose that I don't get the desired benefit. What is my contingency plan? And this is particularly necessary if you accept a certain level of risk, like, okay, I have the constraints, but I can accept a 5% probability that the constraints are not satisfied. I can accept a 5% probability that I don't get any money from this investment, but then it is desirable in some of the cases to make a contingency plan. Like if this really happens, then I can manage in this way. This is a classical step when you present a research project. Usually they ask you to make a list of the risks. Like, for instance, I don't find anybody to hire to perform the research, or my model doesn't work. At the end of the story, I want to develop a model, it doesn't work. And then they ask you for any of the risk, the contingency plan, because they want to make sure that if they give you the money is not wasted. And therefore, they ask you risks and contingency plans, and the reviewers are required to assess them. Robust decision making is very popular, still very popular. And look, in this web pages, it is introduced through a discussion on robust optimization. Robust optimization is can be indeed a robust decision-making problem. So if your decision-making problem involves an optimization, then you get into the domain of robust optimization. There is one thing that I just wanted to make clear to you, because when we talk about decision making, there are several methods. Sometimes the students ask me, "What's the difference?" And in some of the cases, I will discuss the difference, but you don't really have to look for differences. Some of the methods can be applied for the same problem. So the difference may be a detail in the procedure. The difference may be the way you deal with uncertainty, for instance, through probability or through fuzzy logic, but sometimes they overlap. So you don't have to be confused by the fact that I use robust optimization and then I introduce robust decision making. Robust decision making is including, as a particular case, robust optimization. And in some of the cases, robust optimization may be not really a decision-making problem, because when I talk about parameter optimization for a model, it's not really a decision-making problem. It's something that, I mean, like calibration, classifying identification of the best value of the parameter as a decision-making problem is inappropriate. So you don't have just to get confused by the fact these methods look similar, and indeed the concept is similar, but they have been proposed referring to different problems, and therefore makes the different name. But and I wanted to discuss all of them, because in Wikipedia you find robust optimization, but you also find robust decision making. And if you look at the definition, is similar. Robust decision making is an iterative decision analytic framework that aims to help identify potential robust strategies, like robust optimization, characterize the vulnerability of such strategies. Yeah, robust optimization doesn't include characterizing the vulnerability, yes, and evaluate the trade-offs among them. Robust optimization may involve evaluating the trade-off. In particular, if robust optimization is set with respect to two objective functions, then you evaluate the trade-off. Okay, and for these methods, we don't get into analytical details. Okay, so I just described them through a narrative. Okay, and step 1, step 2, 3, step 4, 5, and then here there is a method which is I would like to discuss in detail, because I think it is providing a nice example which basically includes, as a special case, robust decision making. And InfoGap, which was proposed like you see 2001, 25 years ago, after robust optimization, after robust decision making. And what is the idea here? is to assist decision-making when there are knowledge gaps, so there is uncertainty, but here it is also assumed that your model of uncertainty is unreliable. So you don't have a characterization of uncertainty that is analytically expressed. Like, for instance, the example that I gave before, you had the parameter CD, you remember Cx plus dy lower or equal to 10. C and D were varying into a range. And the range, if you want to solve the problem, you have to define it. So uncertainty is quantified through a range. Here, this guy assumed that you are not really sure, so you can't define the range, like C and D vary into a range for which I'm not sure. So one way could be, okay, let's try to define it probabilistically, but actually he wants to use another approach, like, let me estimate what is the max level of uncertainty that I can tolerate. So instead of estimating decision in the face of uncertainty, so I define uncertainty, I get a decision. Yeah, the idea of saying, let me explore the decisions and let's see what decisions are acceptable by studying the maximum level of uncertainty that I can tolerate. I give you an example that gives to you probably a clearer idea. We will also discuss a method that estimates the best decision, not by starting from climate change predictions and selecting the decision. The idea is, let me first select the decision and then estimate what is climate change that I can tolerate with this decision. And this is a different way of dealing with uncertainty. Is the first way conditions the decision on uncertainty for which I have to get a good estimate. The second way is, let me first select the decision which I think works better. And let me estimate if the decision is robust against climate change. If not, okay, I look for another decision. And the same case here. Let's suppose that I know there is uncertainty. This is the idea this guy had. But I can't really make an estimate for it. And this happens in climate change, indeed. Sometimes I know climate prediction are uncertain, but to what extent? And the idea is, I give you the word to you soon. The idea is, let me just look for the maximum tolerable uncertainty in face of a decision. This is the idea. And then there is an analytical development, which we will see. Yeah.
In this method, we don't know any information about the boundary conditions.
No, we may know the information, but what we don't know is the level of uncertainty, okay? And, or we may have some knowledge of the level of uncertainty, but not really final, okay? Not really conclusive. So basically, here you can read, it is a mismatch, this method, between what is known as what needs to be known to make a good decision. And so it says the info gap assists a user that need to take a decision to assess how wrong can the available information be without compromising the quality of the outcome. So basically, I say, okay, this is the decision that is effective up to a level of uncertainty of 20%. Like your future water resource availability will allow you to use this solution up to a level of uncertainty in water resources availability of 20%. If you get an uncertainty that is larger than 20%, this is not working anymore. So basically, it says it evaluates the robustness of an intervention strategy as the max range of information, input data, model parameters, uncertainty, that can be negotiated while maintaining specific performance requirements. This is the idea, which was later on developed by others, but this was a milestone approach in this respect because it solved the problem of incomplete knowledge of uncertainty. And there is another idea of this guy, which he wants also to recognize that uncertainty may be an opportunity. Why an opportunity? Because uncertainty, of course, means that you may get less than expected, but it also means that you may get more than expected. So when you invest money and you make a prediction like, okay, this trade may give to me an interest of 10% annual, there is a risk, so you may get 6, but you may also get 15. And you know that there are some people that mix it. Like if they have a lot of money, they put some money in safe investments and some other amount of money in risk investment, because risk, so uncertainty, means also an unexpected, possible unexpected reward. And this guy said, we have to consider it. So we have also to identify the solution that while minimizing the negative outcome, while minimizing it, gives also the opportunity of getting more than that. And remember the fact of transforming a problem into an opportunity is what makes a difference between a successful strategy and a strategy that is so and so. I mean, what we said during the pandemics, let's take the opportunity. The opportunity was to improve the digital assistance, and indeed, it was a big improvement. Of course, we would prefer not to have had it, but given that it came, it was a big improvement. It was like the First World War promoted an advance of technology that was really a big jump. And the Second World War was the trigger for developing our flying techniques, airplanes, and there was a big jump. Without the Second World War, probably we would get it 20 years later. This is normal because, and of course, we don't want problematic situations. But when we get involved into a problematic situation, what makes a difference between a strategic person and a person that is not strategic is that the strategic person is able to find the opportunities from a problem. And indeed, this kind of idea of saying, I have a lot of uncertainty, I have to consider the downside of it, but let's also take into consideration the unexpected reward, and here it's called unexpected windfall. And I had a hard time to understand what windfall means. And in Italian is manna dal cielo, but I didn't, finding the translation was not an immediate consequence. And because we call manna dal cielo, it was a religious, really, a religious, sorry, prophecy, yeah, and which is something that comes from the sky that you are not expecting. Like a miracle. And windfall is the translation in English. We don't say something literal translation of windfall. We say manna dal cielo. And okay, so we will discuss next week about this. And there is some
Manna del cielo.
Manna dal cielo, yes.
Hand of the sky.
Let me just let's make. We have a couple of minutes, so let me make a very quick search. So let's see how to translate manna dal cielo, and because now we have, and then we will see manna dal cielo, manna from heaven, or I don't think so. Manna from heaven, I don't think it's a good translation. Let's try to search in Google because, you know, artificial intelligence sometimes yeah, let's see, mostra altro. Or reverso, maybe. Manna dal cielo, I think. Yeah, windfall, you see. And but also God send, I like it. And manna from heaven, I don't think it's, but it's also windfall, you see. I couldn't find any sign of that windfall.
Manna is like a gift.
Yeah, manna is a food, manna. Let me just, I I don't know.
Manna is a gift.
Yeah, I think it's a gift. And yeah, I think it's a gift. And let me see, what is manna? Ah, no, this is reverse, sorry. But yeah, I think it's not food. I don't think it is food, but I think it's a kind of a gift. But it's not money, I'm sure. Yeah, it's a miraculous food. Yeah, it's food. Okay, thank you very much. As I said, be patient with the video, but by Friday for sure it will be there. Okay, thank you.
Thank you.
Yeah, bye-bye. Arrivederci.